Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to take up the first numerical on Zener diode as voltage regulator. Let me read out the question first. Part A of the question, for the Zener diode network shown below, determine the load voltage VL, the voltage across resistor R VR, Zener diode current IZ and the power loss across the Zener diode PZ. Part B of the question, repeat part A for the load resistance equal to 3 kilo ohms. Coming to the Zener diode network, note that the input voltage is 16 volt, the series resistance value R is equal to 1 kilo ohms, the Zener voltage is 10 volt and the load resistance is 1.2 kilo ohms. Also, we are given the value of the maximum power dissipation across the Zener diode and it is equal to 30 milliwatt. Let us start with the solution now. I'll start with part A of the question first and let me write down the given values here. We are given the input supply voltage as 16 volt. The series resistance value is given as 1 kilo ohms. The Zener voltage is given as 10 volts. The load resistance is given as 1.2 kilo ohms. And the maximum power dissipation by the Zener is 30 milliwatt. Now, note that the value of the load voltage VL is not given in the numerical. That means that we should now check whether the Zener diode is conducting or not. If at all it was conducting, the value of the load voltage should have been equal to the Zener voltage of the diode, which is 10 volts. But here in part A, we are asked to find the value of the load voltage. So we have to now find whether the Zener diode is conducting. So the question now is how to check whether the Zener diode is conducting or not. To find out this, let us now remove the Zener diode from the circuit and compute the voltage across the resulting open circuit. Let me draw the equivalent circuit for this condition. Please note, I am going to simply remove the Zener diode from the circuit and rewrite the circuit by considering the Zener as an open circuit. Okay, this is the equivalent circuit when the Zener diode is eliminated from the circuit. Let the voltage across the Zener diode terminals now be denoted as V and the polarities will be like this. The upper terminal is positive and the lower terminal is negative. Let us now compute the value of V. If the value of V computed is greater than the Zener voltage, then the Zener diode will conduct and the output voltage will be equal to the Zener voltage, which is 10 volt. If on the other hand the voltage V is less than the Zener voltage, then the Zener diode will not conduct, and in such a case we will find the value of VL by applying KVL to the circuit. Let us now concentrate on finding the value of V, which is the voltage across the open terminals of the Zener diode. The formula for finding V is given by RL divided by R plus RL multiplied by the input voltage V in. The value of RL is given, the value of R, which is a series resistance, that is also given, and the value of input voltage is 16 volt. So let us now substitute these values into the equation and find out the answer for V. RL is 1.2 kilo ohms, R is 1 kilo ohms plus the value of RL again multiplied by the value of input voltage, which is 16 volt. Computing this, you will find the value of V as 8.73 volt. This is the voltage across the Zener diode terminals. Since the voltage V across the Zener diode terminals is less than the value of its Zener voltage, which is 10 volt, we can now conclude that the diode is in off state. Right. So now we have established the fact that the Zener diode is not conducting. Let us now start finding the value for VL. Please note that since the Zener diode is off, the load voltage is equal to the voltage across the open terminals of the Zener diode, which we just computed, and is equal to 8.73 volts. Let us now move on and find the voltage across the series resistance R. For that, let us apply KVL to the circuit as shown in the figure here. So the equation would be V in minus of VR minus of VL. I'll rewrite this equation for VR. So VR will be equal to V in minus of VL. The value of V in is 16 volt and the value of VL is 8.73 volt. Therefore, the value of the voltage across the series resistance R is 7.27 volts. Now, I'll move on to find the value of the Zener diode current IZ. Since we already have established the fact that the Zener diode is off, the value of the current across the Zener diode will be 0. And lastly, I'll find the value of the power dissipation across the Zener diode. The power dissipation across the Zener diode is given by the equation. It is given by Pz and is equal to Vz into Iz. Since the value of Iz is 0, the value of the power dissipation across the Zener diode will be 0 watts. This is the answer for part A of the numerical. Let us now come back to the equivalent circuit and analyze why the Zener diode did not turn on even though the value of input voltage was 16 volt. Please note, I have previously discussed the working principle of a Zener diode in one of my previous videos, and you can watch it by clicking on the link shown in the top right corner right now. In that discussion, we have learned that to make sure the Zener diode turns on, the minimum value of RL should be greater than a certain threshold. So, we understand that the value of RL that is given here, which is 1.2 kilo ohms, is lesser than the minimum required load resistance value. This is the reason why the Zener diode did not turn off even though the input voltage was 16 volt. Right, that would be our conclusion for part A of the numerical. Let us now move on to part B of the numerical, where we are given the value of the load resistance is now increased to 3 kilo ohms. So now we will once again find the value of V, which is the voltage across the terminals of the Zener diode, and find whether the Zener diode now turns on or not. The equation for V is given by RL divided by R plus RL multiplied by the value of input voltage V in. Please note, now the RL value has changed and it is 3 kilo ohms. R value is still the same, which is 1 kilo ohms. And the value of input voltage is still 16. When you compute this, you will find the value of V as 12 volt. Please note, now when the value of RL is increased to 3 kilo ohms, the value of the voltage across the Zener diode terminals is 12 volt and it is greater than the Zener breakdown voltage, which is 10 volt. Therefore, the Zener diode will now turn on and now it will be replaced by a voltage source with a value equal to 10 volt. Okay, let me now very quickly show you the equivalent circuit for this condition. As I said, now I have to replace the Zener diode by a voltage source. And the value of this voltage source is equal to the Zener voltage of the diode and it is equal to 10 volt. Please note the change in the load resistance value. It is now 3 kilo ohms. So now we will once again find the value of VL, VR, IZ and PZ for this new circuit. So let us start with it. I'll start by finding the value of the load voltage VL. Since the Zener diode is now turned on, the voltage across the load resistance will simply be equal to the voltage across the Zener diode. Now, since the Zener diode is replaced by a voltage source here, the voltage across the load is simply equal to the value of the voltage source, which is 10 volt. That is, the value of VL is equal to the value of VZ, which is equal to 10 volt. Let us now find the value of the voltage across the series resistance R. Recall the equation for the voltage across the resistance R in part A of the question, which was VR is equal to V in minus of VL. The value of V in is 16 volt and the value of VL is 10 volt. Therefore, the value of the voltage across the series resistance R will be 6 volt. Let us now find the value of the Zener diode current IZ. Let us come back to the equivalent circuit. Note that the value of the Zener diode current IZ is equal to the value of the current that flows across the series resistance R, which I will denote it as IR, minus of the load current, which I will denote it as IL. So, I will write the equation as IZ, which is a Zener diode current, is equal to IR, current across the series resistance, minus of IL, which is a current across the load. Let us now find the values for IR and IL. These are quite simple. The value of IR is simply is equal to the value of the voltage across the series resistance R divided by the value of the resistance itself. We have previously found VR as 6 volt and the value of R is 1 kilo ohm. Therefore, the value of IR is 6 milliamperes. By using a similar approach, let us find the value of IL, which is equal to VL divided by RL. VL is 10 volt, the value of RL is 3 kilo ohms. Therefore, the value of IL will be 3.33 milliamperes. Therefore, the value of IZ is equal to IR minus of IL, which is 6 minus of 3.33 milliamperes. This is equal to 2.67 milliamperes. This is the answer for IZ. And lastly, let us find the power dissipation across the Zener diode. Once again, we will use the same equation for the power dissipation, which is PZ is equal to VZ multiplied by IZ. Now, since the Zener diode is turned on, the value of VZ is 10 volt and the value of IZ we just computed and is equal to 2.67 milliamperes. Therefore, the answer for the power dissipation across the Zener diode is 26.7 milliwatts. Please note, this value is less than the specified maximum value of the power across the Zener, which is 30 milliwatt. Well, with that, we come to the end of this video. In my next video, I'll take up some more numericals on Zener diode as a voltage regulator. So, stay tuned. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.